astrophysical phenomena. And then I'm going to discuss two approaches, which we are actively working on, which address some of these challenges. One of them is going to be on what I call this quasi-spectroscopic approach. This is for underground astrophysics primarily, where we're trying to measure things at very, very low cross-section. And then the other one is a spectrum unfolding approach, which we've been working on for many years now, which will be very applicable, hopefully, to EFRIT type science. Here's just some pictures for those of you interested, liquid scintillators and various types of detectors that we work on down at Oak Ridge. Okay, to start off, very simply, what kind of measurements can one perform that require detection of neutrons? Okay, so if I have some nucleus and I need to detect a neutron, for example, I can do a gamma N reaction, or I can do a DN reaction, alpha N, for example, PN, and each one of these are unique in the sense that they require some type of information regarding the neutron, either by a counting experiment or some type of spectroscopic information, meaning I need to measure its energy. And these are involved in a lot of astrophysical scenarios, so I'm sure most of you are familiar with this, the chart of the nuclides, the astrophysicist view of the chart of the nuclides, where we overlay all the processes that belong to stellar evolution. So where neutron measurements become important are things like the S process is the most classic example, where, for example, carbon-13 and neon-22 alpha N reactions are the neutron source fueling synthesis of heavy elements in this process. Another one is neutrino-driven winds, and alpha N and actually PN reactions in this region here correspond to production of elements in this so-called light R process. Another application is DN reactions, which can be used to probe P gamma type reactions. P gamma are very difficult to perform, especially with radioactive beams if you don't know the resonance energies. And DN reactions can provide useful information, nuclear information, to constrain these astrophysical rates. Now, there's a problem, and there's a reason why there's not many neutron measurements performed in this type of work. It's because neutron detection is a tricky business. There is no, what I like to say, there's no high purity germanium equivalent for neutron detection. I don't have a detector that I can just use to measure some source and get, oh, that was a neutron at 4 MeV, that's a neutron at 5 MeV, without some other type of information. And this makes detection of neutrons quite challenging. It essentially limits us to two different types of detection techniques. Capture-based techniques, okay? We just capture the neutron in some kind of nucleus, but this destroys all energy information, so I'm now limited to counting experiments. Or I can rely on some type of elastic scattering, and it's typically done on protons. But this is not, one neutron gives you a discrete neutron energy. It results in a continuous proton spectrum from 0 to up to the incoming neutron energies. And this causes challenges as it makes the detection efficiency threshold dependent. And when we talk about reactions which require measurement of neutrons of low energy, this threshold dependence leads to large uncertainties in the detection efficiency when you talk about near threshold events. And this becomes a problem, for example, when we do measurements in inverse kinematics, where neutron energies are typically very low in the backward direction. Now, using elastic scattering techniques, we can actually extract neutron energy, and this is done via time of flight measurement. Okay, so if I have some kind of timing signal associated with those nuclear events, and I know the flight path, I can then determine the neutron energy by measuring its time of flight over that flight path. This is known as time of flight. Here's just the cartoon picture from a Vandal paper regarding that. So we see gamma ray flashes, and then neutron events coming in at delayed times. So basically, this limits us to two different types of detection schemes here. Now, when we talk about experimental conditions, I like to sum up current and future work in nuclear astrophysics as dealing with low reaction yields and high backgrounds. So what I mean by this is there's studies being done at direct measurements, very, very low cross sections, trying to get down to stellar burning temperatures. These are mostly performed in underground labs, where we're trying to measure things at cross sections of picobarns or less. Very, very low yield and high background. And I like to put rib measurements in that same category. And the reason I say this is because we're limited in beam intensity. So we still have the same problems associated with direct measurements where we just don't have a lot of yield and we have to deal with a constant source of background. And I'll address that a little more in a second. Now, for those of you that aren't familiar with the two techniques that I described, I want to cover those in a little more detail. So the capture-based techniques, the idea here is we just capture neutron on some type of nucleus with a high cross-section for capture. Helium-3 is by far the most common. Boron, lithium-6, gadolinium. And these are typically have very low gamma sensitivity, so it's perfect if you have high gamma ray environments. And with these types of technologies, we can have high detection efficiency, near 4 pi coverage. So it's ideal for measuring total cross-section measurements. But the problem with these measurements is the fact that the capture cross-sections peak at very low neutron energy, and this requires thermalization. So basically, if I have some neutron from some reaction, I need to typically collide it off something like hydrogenous material, slow that neutron down, thermalize it so that we have efficient neutron efficiency for the detector. And this essentially destroys all energy information. We're back to counting experiments. And another problem is in the case of multi-neutron emission. Okay, so some of these reactions can produce, for example, N2N and 3N. And in order to extract reaction cross-sections from data with counters, we need to rely on simulations to understand what was the probability that this was a double neutron, a triple neutron event in some of these counters. To give you an idea, for those of you who are not familiar, these are two examples. This is one located here. It's a large capture detector. There's other ones used which look a little different. So this is a measurement of carbon-13 alpha N. This is not using a gas detector, but what it's actually using is a cadmium capture with the gamma rays associated with the capture detected in a barium fluoride array. But the idea is the same, right? We thermalize a neutron, we capture it, and then detect the associated particles. But we lose all energy information in this process. Now, the other way we can detect neutrons is via elastic scattering. So this usually relies on NP scattering in hydrogenous materials. And if your hydrogenous material happens to be an organic scintillator, for example, we can then produce light in those types of events. Now, because we're dealing with scintillators, these are gamma sensitive. So we have to be able to say something about, was that event a neutron event or a gamma event? Pulse-shaped discrimination, which is an ability of a material to distinguish between nuclear and electronic recoil events, is an extremely useful process in this because we can say something about the particle that create that scintillation event. And that's, here's just a picture of it. So nuclear recoils typically live a longer pulse than a electronic recoil. And if you're more interested in this, I can talk about that in much more depth later. And we can get the energy by a time of flight measurement, right? So for example, an FRIB or similar facilities, right, where you have beam pulsing, we can measure the neutron energy spectrum from the time of flight associated with that. But because these are not thermal detectors, we have a threshold. And typically, these are limited to neutron measurements above 100 keV, if we're just detecting just pure time of flight events. And if you need to use pulse-shaped discrimination because you have a high gamma ray background, for example, 500 keV is kind of a good ballpark of the threshold here. What do some of these look like in practice? These are liquid scintillator bars, time of flight detectors, 2 PMTs, position sensitive. They're liquid scintillators, they have PSD capabilities, one example. Another one is the Vandal array, which is just a dual readout classic scintillator array, time of flight measurements again, but this is a no PSD detector. And then we have our liquid scintillator cans as well. These are PSD liquids, can be used in time of flight mode. Just to give you an idea of what the experimental setups of some of these actually look like. Okay, so now we covered why neutrons are difficult to detect, some of the technologies available to us as an experimentalist. And now we need to talk about what types of measurements can you perform. And I break them down into kind of 2 categories. This is general, very general categories. And one of them is the use of stable beams, very high currents, underground astrophysics. Now, unfortunately, these measurements are typically performed with DC accelerators. No time of flight is available. So we can't say anything about the neutron energy. And this is really an unfortunate situation that we find ourselves in, but is the state of the field currently. And typically, helium-3 counter measurements are used. These are counting experiments. So they have to you have to go underground to deal with the backgrounds associated with these measurements. And the reaction of interest are kind of S-process nuclei, carbon-13 alpha N, neon-22 alpha N, and maybe magnesium-25. We'll see how that goes. And the big name of the game here is how do we discriminate between signal and background if we're just doing a counting experiment? We'd have no time of flight. We have no information about when the reaction occurred. The other type of measurements that a lot of us are interested in is measurements with RIBs, rare isotope beams, radioactive beams. These are typically low beam intensities. Even if we're doing good, we might get 10 to the 6, 10 to the 7. It's still statistics limited in many situations. But fortunately, beam pulsing is available at these facilities. I don't know of any RIB facility that does not have beam pulsing available. So that means we can measure neutron energy. We can also say when the events occurred, which helps discriminate background. But the problem here is the beam's radioactive, production targets are radioactive. For example, if we're measuring an in-flight facility, anywhere near the in-flight production target, you're dealing with huge gamma ray backgrounds. And then we still, of course, have the terrestrial backgrounds. And here we're trying to detect neutrons kind of in the tens of keV to tens of MeV. So we need a reasonable dynamic range, which means we need a long flight path, our efficiency drops. To give you an idea of what one of those measurements would even look like, this is one we did at Notre Dame a few years ago, about a decade almost ago now, with fluorine-17 DN. And what you see is here's a time of flight plot, like I showed before, and the light output of it. So this is kind of proxy for the energy. And we see the gamma ray events, and then we see nothing else, just this complete gamma ray background, right? And if we want to actually extract those neutron recoil events, we need PSD in this case. And once we use that PSD threshold, the neutron events pop out of this background. But you see, these are all gamma ray leakage and neutron events, which are just background. So if we didn't have PSD in this situation, it makes this measurement unfeasible. So these are the kind of scenarios where we can make improvements. And with that, I want to talk two different topics. I want to talk about a quasi-spectroscopic approach, which is targeted toward underground astrophysics measurements. And then I want to introduce something known as spectrum unfolding, which is going to be related to RIB-type, effort-type physics. Okay? Is there any questions on the background before I jump on?
Well, there are some experiments. There's some accelerators.
High current? It's high current, but the energy is way too high to perform these type of astrophysical measurements. Now we're dealing with like, you know, sub-MeV level experiments.
What kind of timing?
Honestly, if we even had microsecond timing, this would help. Any kind of timing would be beneficial. Unfortunately, none of these labs have done it. And I don't know why that's the case, but okay. So the first topic I want to discuss is a quasi-spectroscopic approach. And the example I'm going to use is carbon-13 alpha N, because this is a really nice test case for this. There's a lot of interest still in the field on this. Carbon-13 alpha N is the main neutron source for the slow neutron capture process, or the S process. And it's really the driving force for synthesis of about half the elements from iron to bismuth and AGB stars. And the current best measurement to date is this work of Heil et al. In 2008. And the conclusion of his paper said, it looks like the technological possibilities of doing these measurements above ground have been exhausted. And he argues that any remaining uncertainty can only be done in underground laboratories. And this is what the community is doing. There's facilities in Italy. There's doing an upgrade, Luna MV. It's a new upgrade. This is under the mountain in Gran Sasso. There's the Caspar facility in South Dakota at SURF. It's about 4,800 feet underground. And then there's a proposed facility in China, JINA, which is being constructed, and all of these labs are trying to address this and many other cross-sections near stellar brain temperatures. Now, 2 points I want to make about this paper. It's very, very good work, but it's a neutron capture experiment. So there's no time of flight information, no energy information. And that means that you have to deal with these types of backgrounds, which I'll discuss in a second. This is a picture of the Caspar facility in South Dakota. If you ever get a chance to go there, it's a really amazing place. and then the Gran Sasso Luna facility. Here's the world data on carbon-13 alpha N to date. And you can see current measurements are about 100 keV or so from the actual astrophysical relevant energies, which means extrapolation is required to estimate the reaction rate. And this is over multiple orders of magnitude. And this extrapolation is complicated by the fact of a near threshold resonance, a 1/2 plus resonance, whose influence on the projection is, the extrapolation is still uncertain. There's been some measurements using Trojan horse methods at the Catania group, but nonetheless, I think we should be pushing lower and lower in cross section to try to measure this astrophysical rate. So how do we get down there? How do we measure 3 orders of magnitude lower? Oh, another point I want to make about this. I do neutrino physics a little bit on the side, I would say. To give you an idea of how low in cross-section this is, there was a measurement recently done by the coherent experiment to measure the first observation of neutrino nucleus elastic scattering. That measurement was on the order of tenths of picobarns. Tenths of picobarns. When we push down into the stellar burning region, that cross-section is lower than the neutrino nucleus cross-sections on iodine. So these are very challenging measurements. I think that's an interesting piece of information. So one of the ways we could approach this is, let's forget this counting-based experiment for a second. Let's try to say something about the neutron energy. So one way we can do this is using liquid scintillators, organic scintillators, detectors. Because remember that by doing an N-peak reaction or some type of scattering reaction, that proton contains some information about the incoming neutron, okay? So let's take carbon-13 alpha N, Q value is like 2.2 MeV. So that immediately puts an upper limit, a kinematic limit, in the recoil proton spectrum. Any event which occurs above that limit is kinematically forbidden. We can exclude those from our data. Okay, so you're already getting rid of this background up here. Now, on the lower end, all the thermal neutrons, right? Organic scintillators are typically sensitive to about 100 keV or so and above. So everything below that is removed from the data set. Now, if we don't have time of flight, we're going to have to rely on PSD. That's going to push our thresholds a little higher. But any events which are below this are vetoed out. So now we're only looking at background in this small region of interest, right? This is the idea that, like, for example, Majorana demonstrated and other neutrinos, double beta decays, that you win by resolving power, by looking at only a small window. So we brought this question to a group at Oak Ridge and said, can we use this approach to push the cross-section lower above ground? Let's try it above ground, and then let's see if this is applicable to underground astrophysics. So to do that, we need some type of neutron detector. Thankfully, we were already building one for a different application. This is known as the SABRE bars, a scintillating array of bar detectors for reaction experiments. Now, originally, these are designed as time-of-flight detectors, kind of very similar to Vando or Lenda, which is located here. But the difference is we have pulse shape discrimination. So these are liquid scintillator detectors, dual readout, so PMT, PMT, we can tell position sensitivity. Here's a plot of position sensitivity. It's about 1-inch resolution for neutrons by doing the dual readout. And these are completely filled with liquid scintillator. This port on the side is actually for the expansion bubble. So one little subtlety about liquid scintillators is when you build one and they're sealed systems, as the temperature fluctuates up and down, you need to be able to account for that pressure buildup. And the way we do that is by an air bubble on the side. So that's kind of an important feature of these detectors. The liquid scintillator is actually made in-house at Oak Ridge. And here's a plot of PSD. So this is the neutron related events and gamma ray related events for looking at DDN reactions. So this is 2.5 MeV neutrons. So we have a detector that we could use to perform this measurement. Now we need a facility. And luckily at Oak Ridge, there is a lab which few know about, I would argue, called the Multi-Ion Research Facility, or MERF. This is an atomic physics laboratory located at Oak Ridge. What's unique about this is it has 2 ECR ion sources. One of them is on a high voltage platform. So this is some of the specs of MERF. Variable frequency machine, max accelerating potential 280 kilovolts, plus we can add 30 kilovolts to the ECR itself. And we typically we can generate beam currents of 600 well, we've been up to about 1 milliamp on protons, hundreds of microamps on helium 1+ and 2+. What's another interesting thing about MRF is if you notice, the analyzing magnet is actually pre-acceleration. And for those of you who've done astrophysics measurements, in particular excitation functions, where you have hysteresis in magnets, this is actually quite a nice feature, because the only thing that I need to change when I'm just scanning over resonance energy is just the accelerating potential. And then all the ion optics after that are electrostatic elements. So I don't have this hysteresis associated with magnets. So this is kind of a nice way of doing excitation functions. Another useful feature at MRF is this other ECR source. It's much lower energy, but what we actually ended up using for is production of implanted targets. So these are very high current measurements. We're trying to measure picobarns. Targets have the best targets that can handle that kind of beam current are ion implanted, and there's a second ion source there which can be used for that purpose. Here's the experimental setup at Oak Ridge. Here's the array. So remember, this is a very low count rate experiment. We're trying to measure down to picobarns. So here's the liquid scintillator bars, precision sensitive, PSD bars. We configure them in a barrel array, water-cooled target, because the high beam currents. And then we surround this thing with about 700 pounds of water bricks and high-density pellets to try to reduce neutron background. And then we have muon vetoes overhead to try to veto shower events, which might produce neutron recoils. Okay. Now for the targets themselves, these are actually ion implanted, so we're dealing with hundreds of microamps here, stopping in a target. So these are producing many, many watts, tens of watts, hundreds of watts in some situations. The way we do this is we have a copper disc, which we electroplate in gold. Gold is chosen because we can produce very clean deposited gold layer, thick enough to stop the alpha beam to reduce beam-induced background reactions. And then here's a view. This is a carbon-13 P gamma resonance scan of the target before and after proton irradiation, 2.5 coulombs of integrated beam on that target. Just advertisement for MRF. We can actually produce many implanted targets there. We have approval to produce magnesium-25 targets, for example. They made iron beams, they made titanium beams, tungsten beams off of the ECR source. So we set all this up, and here's the first data that we took. So another thing about MRF is we do have beam bunching, but it's at the millisecond time scale. So this is not so useful for time of flight, but it does allow us to continuously measure the background throughout the progression of the experiment. And here's what we've seen. Beam off data and beam on data. With carbon-13, this was taken at 500 keV alpha energy, well below the Coulomb barrier for that reaction. And we've seen an excess of neutrons right about the energy we expected. So it looks like this technique is working. Now, unfortunately, things aren't this simple. And this is where I really want to stress the importance of having some type of energy information. If you look at this data more closely, this is carbon-13 alpha N. What is this? There's an increase in high energy neutrons. And this took us about a week to figure out what this was. Turns out that alpha beams are often contaminated with deuterium. So we looked up a paper from Luna, and they claimed that their contamination level is 10 to the minus 7. And you go, oh, 10 to the minus 7, that must be an incredibly low probability of getting any kind of neutrons from that reaction. Turns out carbon-13 DN reaction is 7 orders of magnitude higher than alpha N. And what this means is that these two are actually going to compete in counts as we go lower and lower in cross-section. If you didn't have any kind of energy information, you would have no idea that these events are occurring. And just to give you an idea, if you have a helium-2+ beam, D+ is your contaminant. If you have a helium-1+ beam, molecular deuterium is a problem. And another important point I want to make about this, you can't just run on blank, because this is coming from reactions on carbon-13. If I just run a gold foil blank, I'm not going to produce this type of signal. So this is kind of interesting, right? Because we're trying to measure low, and if you remember from the previous slide, we're trying to understand the influence of this near threshold resonance. If all of a sudden my dn reactions start overtaking my alpha n, my S factor is going to start increasing, and I'm going to wrongly interpret this as a width on this resonance. Okay, so after a few months of figuring out how to deal with that, this is our current data set from that. So these points in red are the measurements at Oak Ridge compared to the world data set. So I would argue that we are competitive to the lowest measurements to date, with significantly improved statistical uncertainties. And we argue that this technique should be produced underground, right? We should use these kind of quasi-spectroscopic approaches when doing these types of measurements. We should avoid counting experiments in these types of measurements. So we went underground at SURF and took some background data, and I was surprised to find another source of background, which is another problem, another reason why we should be using some type of energy information. And that background comes into effect in gamma-induced neutrons. So when we talk about underground astrophysics, right, the idea is we have very, very low counts, very high background. And one of the things that occurred to us when we were down at Caspar was, in addition to the commonly accepted neutron sources in the walls, right, fission and alpha n, there's also the gamma ray flux down there is much higher than on the surface. And in particular, thallium-208, 2.6 MeV. 2.6 MeV is above the breakup energy for deuterium. Now, why is that important? Remember, a thermal neutron detector requires moderation. Remember, we talked about this. We have captured material in some kind of hydrogenous medium. Hydrogenous mediums contain deuterium at the 1 in 5,000 level. Okay? Gammas from the surrounding medium can break the deuteron up and produce neutron signals. Okay? The cross-section for that is in millibars. So here's an example. This is a helium-3 counter, which is currently at Caspar. We measured the gamma ray rate, the thallium-208 gamma ray rate, and if you take that rate and you propagate it through this the helium-3 counter, this is the level of background produced from gammas breaking up natural abundance of deuterium in hydrogenous medium. It's right exactly at the level where we're trying to measure astrophysically relevant cross-sections. And if we're off by a factor of 2 in the gamma rate, this would be the influence here. This could be easily separated if we have some type of energy information. We're coming in at 2.6 MeV, right? The breakup threshold is 2.2 MeV. There's only 400 keV of energy. If I then split that between the proton and the deuteron, or the proton and the neutron, it's a 200 keV neutron. It's below threshold if we use a liquid scintillator. It is not below threshold if we use a counter. So this should be taken into consideration. I mentioned JINA, this underground lab being proposed in China. Now they have a very different philosophy on their counting system. Instead of just having polyethylene as the moderator, they're actually surrounding their detector in liquid scintillator, using that as a moderator. Now what's interesting, what I think is interesting about that, is, remember, 200 keV proton is still detectable in organic scintillators. So you could actually use that, say, oh, there was an event, a recoil proton event, I'm gonna wait for the neutron to capture. If I see that signature, that might have been a breakup reaction, I should veto that. So that can be accounted for. But if you didn't have that type of information, that type of veto system, you could be easily fooled that the cross-section is higher than you expect it to be. Now, of course, this is very easy to deal with. We can surround our detectors in lead, but you need to know what you're looking for. So there's one example of why we need some type of energy information regarding the neutron when performing these very low count rate experiments. The other one I want to bring up that we've been working on lately is known as spectrum unfolding. This is more applicable to like effort type science, and I'll explain that in more detail. So I keep saying that recoil elastic scattering detectors are often based off of hydrogen, but one interesting thing is you can replace all the hydrogen with deuterium. What does that do? If you look at the cross-section for elastic scattering, hydrogen is more or less isotropic in the center mass frame, but deuterium has a strong peak at back angles. So let's consider, if I have a neutron source that's emitting 3 energies, right, and a hydrogen-based detector, I'm going to get some kind of recoil spectrum look like this. Remember, neutron comes in, I produce a continuum from 0 up to the incoming neutron energies. If I convolve this with detector resolution, I get kind of this featureless spectrum here. But because of the enhancement at back angles associated with ND scattering, I get these what we call recoil peak features, which say something about the incoming neutron spectrum immediately. Now, by switching all the hydrogen out for deuterium, I don't change any of the properties of that material. I still can do pulse wave discrimination. I still have fast timing, so it's still useful for time of flight. One interesting effect actually is the N-gamma cross-section is actually lower at hydrogen than deuterium. So if I have germanium or other materials around, I'm not having a lot of capture background in these detectors. But the one I want to stress is that we can obtain neutron spectroscopic information without use of time of flight. So when we talk about underground astrophysics or facilities that don't have timing or limited timing information, we can still say something about the neutron energy spectrum. And what this allows us to do is put detectors very close to the reaction targets, maximizing our detection efficiency without loss of detector resolution. So again, it's kind of this common trend. We need to know more information about the neutron energy spectrum. This is a DDN, so this is 2.5 MeV neutron. This is a recoil proton spectrum, and then recoil deuteron spectrum for 2.5 MeV neutrons. And you can see that recoil peak-like feature immediately. Now we've been working on. Huh?
What kind of energy resolution is that?
I'll show you. Yep. Now we've been working on deuterated scintillators for quite a while now. This is my thesis work. We started with deuterated benzene base. We moved on to xylene base because these ones are carcinogens. These ones are still flammable. So then we moved into solid, and they're liquids, and there's some questions about it, using liquid scintillators. So we worked on the deuterated stillbeam. That works beautifully, but it's horribly expensive. So then we moved on to toluene and naphthalene-based materials. So we have a long history in deuterated scintillators, and these are mostly now becoming homemade materials. This is some examples. This is deuterated toluene scintillator. This is basically paint stripper, for those of you familiar with that. This was the first deuterated stillbeam single crystal. We have 2 of them now. That one's located at Oak Ridge. And then that was actually, you can't actually buy deuterated stillbeam, so it had to be synthesized from deuterated styrene, actually, using a Grubbs catalyst, which actually won a Nobel Prize in chemistry quite a few years back for that reaction. This is some of the PSD performance of deuterated stillbeam versus stillbeam. If you notice, the deuterated stillbeam has a slightly improved PSD because the energy loss of a recoiled deuteron is higher at DDX than a recoiled proton. Okay, so how do you actually do spectrum unfolding, right? I just showed you that if we take like 3 monoenergetic neutron groups, we create these kind of recoil peak features, but how do I take that and get some usable energy spectrum? So I want you to consider this for a second. Let's take 2 neutron energies, A and B. What I observe in a measurement with one of these detectors can be treated as simply this incident neutron spectrum acting on some type of response matrix, or the relationship between light and energy in the detector. And this matrix creates some kind of detector response, right? So there's the 2 recoil peaks, and this is the incident spectrum that created that response, right? So we can just write this implicitly. So here's the measurement. If I know the response matrix, right, if I could invert this matrix problem and then extract the neutron energy spectrum that created that response. That's the basic idea here. Now, unfortunately, these response matrices are very opposed. You can't simply just invert them, but we can still use something like a maximum likelihood technique to extract the neutron energy spectrum that created this response.
You're saying that response is very nonlinear.
Yeah, oh, exactly. You have the Burke's effect, and then you have cross-section effects, and then you have multi-scattering if they're larger detectors. So typically, we experimentally measure these response matrices.
You cannot model them.
You can, and you can do reasonable, but if you're trying to talk about precision measurement, especially in the low energy, remember I showed you that the neutron efficiency can really affect your extracted yield. You really need to measure this thing. Okay. So this is what I get in the measurement. If I then apply some kind of maximum likelihood algorithm, for example, I can then unfold this incident spectra that created that response. Okay, and here's an example. This is deuterons on a carbon-13 enriched CD2 foil, or CH2 foil. This is the measured spectrum. And what's unique about these materials is I can immediately say something about the neutron energy, right? I see all these recoil peaks features, which says something about the neutron energy spectrum that created that response. If I then know the response matrix for a detector, I can then unfold this and get an extracted energy spectrum. And now everyone's comfortable with analyzing this. And this is done without time of flight. This is just simply, I have a source, a detector, I know the performance of this detector very well, I measure that response, and then I can unfold the energy spectrum that created this response. And what's neat about this is this really only depends on photon statistics. So when I compare the resolution of different measurement techniques, time of flight, of course, is going to get, your energy resolution is going to suffer as neutron energy to go up, right? Because I'm at a fixed distance, right? And I have some timing resolution. And the time of flight, what's the uncertainty of the flight path governed by that timing resolution? The resolution is going to get worse and worse. But in unfolding, it goes like the photon statistics. So then what this allows me to do is if I have one of these detectors, remember, none of the other performance parameters suffers. It's still a liquid scintillator. At low energy, I can use time of flight. And high energy, I switch over to unfolding. And by combining these two together, I have something that has a fairly high efficiency, maximizing the physics you can extract, for example, with radioactive ions. This is the thought behind this. Here's more examples of unfolding. These are spectrum unfolded, carbon-13 DN, boron-11 DN. These are 16 MeV beams, deuteron beams, fairly high energy neutrons in the 20s of MeV. These are energy cross-sections that were extracted by a measurement of 50 centimeters from the target. No time of flight.
This is your still beam detector.
This was actually done with deuterated benzene. The still beam would be even better, but right now it's limited to very tiny crystals. Here's a very complicated spectrum, a Pubi source, right? There's no timing information there. This is the measured spectrum, and this is the unfolded neutron spectrum. Another case, carbon-13 helium-3n, or carbon-12 helium-3n. Measured response, unfolded spectrum. These are 13 MeV neutrons measured 50 centimeters from the target. So how does this apply to astrophysics? Well, we don't have the rib intensities yet to do these types of measurements. That's hopefully after will give us that. But we can still look at this technique in other cases in astrophysics. And one of them, which Michael Vischer approached me about, was boron-10 alpha N. They've been trying to measure this as a possible background in underground astrophysics measurements. It's common contaminated targets. Now the data is currently limited to about 1 MeV. Remember, most astrophysical scenarios are trying to measure below an MeV. So we need data down in those regimes. Now, Notre Dame tried to do this measurement multiple times using helium-3 counter, but they failed because their cross-section always ended up looking like boron-11 alpha N. And if you look at the enrichment of the target, it was 94% boron-10 enrichment, but the boron-11 cross-section is so much higher that you just cannot disentangle boron-11 and boron-10 events. Remember, helium-3 counters destroy energy information regarding the neutron. And then at Notre Dame, these are low cross-section measurements, so we need high current machines, and unfortunately, the current state of the field is we don't have time bunching at high current accelerators. So one solution was the deuterated liquid scintillators. We can extract boron-11 and boron-10 events from these. This is experimental setup. So for those of you who have been in Notre Dame, this is the business end of the 5U accelerator. These are the deuterated liquid scintillators, and then we just put a germanium in there, helps us disentangle some background type events. This is the PhD work of Chen Liu at Notre Dame, a phenomenal student who did a lot of this work. So again, here's a PSD plot from one of those measurements. This is Oak Ridge formulation, deuterated benzene, gamma ray events, neutron events. This is the recoil spectrum from that. And then we can unfold this to get the incident energy spectrum of the neutrons that created this response. Remember that idea? Okay, so if you look at this, kind of interesting. So here's the boron 11 events. This is the boron 10 events. This is carbon 13 alpha N events. So in a beam line, right, there's pump oil, there's fingerprints, there's always carbon around. And this always produces carbon 13 alpha N neutrons. It's just a fact of life that we have to deal with. If you didn't have any energy information, this would just be a background you'd have to deal with constantly. But using spectrum unfolding, we can just get rid of that completely.
The background is so low. Subtracted something.
No, no.
You count for every count in the lower spectrum.
Yeah, so one of the requirements in the unfolded spectrum is neutrons are not created nor destroyed. Statistics are the same.
One reason I was surprised your background was small. It looks as though you don't fit the spectrum very well.
So, okay, so this was a simulated response matrix. That's the importance of measuring these things. So at the end of the month, we're going to Ohio to measure low energy response.
So you tell me, you gave me one of those spectra and I simulation set a little bit of some other people that you find them.
Yes. High probability, I think we could probably find it. If you get hundreds of counts. I can't do this on 10 counts. And what Chen was able to show at Notre Dame, which I think is quite impressive, is measurement of the boron 10 alpha N cross section below an MeV. So this is the previous data set measured with helium-3 in black. This was the Notre Dame measurement in blue. So what we're able to do is we're able to go 4 orders of magnitude lower in cross section without time of flight, measuring boron 10 and boron 11 alpha N. And what's interesting, James DeBoer did this work here, is looks like we're on the slope of a new resonance in boron 10 alpha N, which is quite nice work, all because of spectrum unfolding. So I think that's a nice application of this. Now, unfortunately, I wish we could show this for radioactive ion beams, but we need beam intensity, right? This is not a statistics limited scenario. But if we had 10 to the 6, 10 to the 7 particles per second, I think we could do this. So
how do these
yeah.
These detectors age? You have to measure your response periodically.
Yeah, so I know how the detectors that we make because I know all the ingredients that go into them. We don't see aging on the order of 5 years. That's as long as they've been around. Yeah, maybe in a decade we'd have to start remeasuring response matrix, but on the order of 5 years we don't see any problems. That's one benefit of making the liquid scintillators yourself is we know exactly what's in them. We measure all the properties. We know the masses of all the components. Everything is known. When we get materials from vendors, it's this idealized specs that we look off the website, but of course it's going to be batch to batch differences. And when you're talking about spectrum unfolding, where you do need to know the shapes quite accurately, I think that's important. So what's the next step for us? Luckily, we have secured a little bit of funding to develop not a couple detectors here and there for R&D purposes, but an actual dedicated array. So this is some of the cells that we're constructing. We have 12 cells right now, 3-inch diameter, 2 inches deep. We're going to use an in-house deuterated liquid scintillator again. But these will allow us to have a dedicated array of detectors that are ready to go. If people need measurements done, or we want to do some type of neutron producing measurement, we have a dedicated array. This will be characterized at Ohio at the end of the month. So I'm very happy that this is progressing so nicely. Now the idea behind this array is to go after RIB physics, of course, radioactive ion beam physics, and we're going to use this hybrid time of flight spectrum unfolding approach. So we're not going to back the detectors way up because the neutron energy is too high. No, no. Put the detectors close. The low energy part of the spectrum, which is difficult to unfold, we use time of flight. And when the neutron energies become high enough, let's say I have a bunch of isolated peaks. If this peaks contain 2 neutron energies in, I gate that, I project the spectrum, and unfold it. So this is what I say a hybrid time of flight spectrum unfolding approach. By doing that, right, I'm maximizing my efficiency, and I'm not suffering on resolution. The other important point of this, if I back my detectors up and make them larger, they accept more background. So my signal to noise is improving by doing this as well. So that's why I argue for this time of flight spectrum unfolding approach and maximizing efficiency without loss of resolution. And the idea is that arrays like this Hopefully we can build more of these cells. We'll be ready for day one effort type experiments. If you measure the response matrix, we're testing on various scenarios, we should be ready.
If you get to really know the response as well, what do you think your resolution would be for 1 MeV neutron?
1 MeV neutrons probably at 10%. Yeah.
How do you calibrate it? I mean, you use the photo tube, so you turn it on and then you have to take your voltage very precisely.
Yep.
And how do you calibrate it?
So the previous detectors, you can't see them in this picture. They have fiber optic inputs. So we're constantly firing light signals in some of these. We do constant calibrations. On these detectors, they don't have fiber optic ports. I use single PE. I'm always monitoring what is the gain of a single PE in the tail of a scintillation pulse. And this tells me about the stability, the gain stability of the tube. Right? We're trying to do precision measurements, so all of our work is down in the single PE regime. And with improvements in digitizers, when we talk about 14 or 16-bit systems, I can see single photoelectrons detected in a tube. So this allows me to check the gain stability of these
You know
systems.
the ND cross-section well enough to make that, given that you have the 50 spectrum.
The ND cross-section?
So once you have the ND cross-section, you have the recoil spectrum too. So it's the same shape.
Yeah.
So I was wondering if you fitted that in your normal sheet, you fitted the cross-section?
No, we just measure the response matrix is basically the idea. Yeah. I mean, the early days we used to simulate it with MCMP and stuff, but there's always these issues with the unfolded spectra. Of course, if for measured responses, these widths improve significantly. Okay. So in conclusion, neutron measurements are, I don't think I need to stress this, but neutron measurements are an important aspect of experimental astrophysics. Not only total cross-section measurements with counters, but also differential cross-section measurements. All of this benefits from having some type of information regarding neutron energy. Now, I argue that we need to have neutron detector technologies up to par to utilize the capability of current and future facilities, meaning effort and underground astrophysics, right? We spend so much money breaking these accelerators underground, and then we put counters in front of them. And then as I showed two examples of just two backgrounds that we found in the last year, couple of years, but there might be more. And saying something about the energy is so valuable in these types of measurements. So I argue that neutron spectroscopy is really key here. And I gave you two approaches, the quasi-spectroscopic approach and the spectrum unfolding approach, where we can combine neutron time of flight and spectrum unfolding to get more statistics, high resolution measurements, without suffering signals to noise, suffering on signal to noise. Okay. With that, I want to thank my collaborators. University of Notre Dame works very, very heavily with me in all of this work. I mentioned Chen Liu as a graduate student in that group. A lot of that boron work was hers. Very grateful for that. Fred Piketty at University of Michigan, he's the one that started all of this. So yeah, he deserves credit. And then of course, Frank and Michael Vischer and all of those at the Caspar facility for letting us perform measurements down there. Thank you.
Okay, we have time for more questions. Yes.
What is the efficiency of your can you calculate?
The efficiency for these deuterated detectors, it's the ND cross section is a little bit lower, so it's about 10–20% lower than a hydrogen detector.
But how do you know that?
Oh, many ways. The cleanest way we've done it in the past is you take a thin deuterium foil, CD2 for example, and we tag the recoil. So we do DDN. We tag the recoil helium-3, which allows us to produce a known flux of neutrons, and then that's what we measure it that way. Ohio, for example, has a known neutron flux beam. We also have fission chambers that we use. Did I include it? Oh, there we go. These are beautiful devices. This is an Oak Ridge invention. It's a Californium-252 fission chamber. And I could tag each fission event. I know how many neutrons are produced. And then I use time of flight to, this is actually looking at the signals out of the proportional column. But I can use time of flight to calibrate the detector that way. This thing's actually quite neat. It's the size of a little BNC button. It's a fission chamber, fully functional.
Yes, I'm wondering, you mentioned very briefly the possibility of performing, say, for example, the alpha carbon-13 reaction using some kind of Trojan horse approach. What are the limitations of the problems? Why isn't that not maybe working as well?
I'm not an expert in that. I'm not sure why those, what the limitations on those measurements.
One could do that either for the direct reaction and for the inverse, right?
Yeah, and those have been done.
DP alpha reactions, for example.
Those have been done, and I know the Catania group has worked heavily on that, trying to address the, go back to that section. They're trying to address the influence of near threshold widths, for example. But I've been mostly focused on neutron convection side problems. I think it's best if we just measure it directly. We're so close.
Well, then of course.
And then we can test the theory on the beautiful test case.
But there are also been like recent developments, right? To use like gamma reactions to induce. So that would be some kind of an application.
Yeah.
Generalization of the method.
In terms of law, and obviously you're going to have to make screen corrections.
Oh, screening corrections. I don't think for carbon-13 alpha N, the screening is too much of an effect. I know for, well, yeah, carbon-13 case, I think we're high enough in energy, should be a problem. Mm-hmm.
So in your spectrum unfolding, you said you were measuring the response patterns.
Yeah.
What do you exactly do?
What do we measure? Yeah, I guess either one's fine. So what we're measuring is we take, for example, a simple measurement that you can perform is we have a detector and we have a white neutron source. What I mean by white is it's a broadband neutron source. And using time of flight, I can then slice the spectrum, right? Using time of flight, I can then slice the spectrum up to get the light response spectrum associated with each neutron energy. And then in doing that, I'm measuring this response matrix directly. Does that make sense? That's what we're measuring. It's the relationship. We know the energy. What is the light response for that given energy?
What would be the uncertainty in
Huh?
What would be your uncertainty in this method? How do you?
Well, so that's why we go to places like, so the uncertainty in a lot of these is actually, mostly it's the timing. The timing resolution of the system. So it's timing and path length. So the way we get around that is to improve your energy resolution, you just have to back the detectors up significantly. Because there's nothing you can do about the timing, you can do something about the position. So we go to places like Ohio with a long time of flight tunnel, we can get many meters from the target. And then that cuts down the uncertainty in this.
Okay, one last question.
So highest energy. Highest neutron.
Oh, that's an interesting question. So, did I include that slide? So this is interesting. This is 14 MeV neutrons. So one problem with this method is if you give significantly above 10 MeV or so, the deuteron starts to break up. Right? It breaks up above 2.2, but the cross-section really turns on above 10 MeV. So if I take 14 MeV neutrons, this is actually a PSD plot, deuterated still beam, 14 MeV neutrons. And what you're seeing here, this is a complicated spectrum, you're seeing electron recoils from gamma ray events, deuterons, there's our recoil peak, really nicely resolved. And then you see this. That's deuteron breakup. Now, thankfully, we're getting very good at purifying this scintillator material such that we always can generally extract the recoil proton events from the deuteron events. But this does place an upper limit on detection efficiency, of course, because we start getting this contamination. If, for example, if your scintillator becomes too large, you can't resolve proton recoils and deuteron recoils, then you're going to contaminate your matrix with these events, and that'll massively unfold. So there is an upper limit to this. It's a couple tens of MeV. We've measured up to 45 MeV neutrons at Notre Dame actually before, and these are still separated. I mean, this gets better and better as you go on, but the cross section is dropping. Scattered cross sections. This is not competition. These are actually alphas from N alpha. Resolve. Figure of merit in this case, we do a cut here. 7.4, for those of you familiar with the figure of merit. 7.4 for the deuterons and the electrons, and for protons and deuterons, it's 1.4. So a good PSD material is generally viewed as something above 1.2.
Okay, now let's thank Mike again.